Welcome to Lesson 5 of the application of the cost of land and wetland degradation. In today's lesson, we'll cover other three models: the flood control model, the terrestrial product model, and finally the waste water purification model. Welcome. Under the flood control model, we must understand globally the increase of flooding during the recent decades necessitates us to understand the flood impacts and consequences. This is according to a paper that was written by Gall in 2016. We must understand, therefore, that wetlands play a significant role in reducing frequency and intensity of floods by acting as a natural buffer, soaking up and storing significant amount of flood water. The wetland does this in two ways. We have the coastal scenario where the wetlands in particular serve as storm surge protectors when hurricanes or tropical storms come ashore. Then we have the second scenario where peak flood flows have passed, wetlands slowly release the stored waters, reducing property damage downstream or inland. And that is why we are saying that by holding back some of the flood waters and slowing the rate at which this water enters the stream channels, wetlands can reduce the severity of downstream flooding and erosion. Some of the areas that you find flooding to date is because maybe the wetlands that were there were converted into other ecosystems, possibly maybe croplands, or even maybe became urban areas. So you find the ecosystem that had been placed naturally to slow down the movement of water within some of these water channels, like the scenario that we have in Kenya of River Nyando that always bursts in banks and causes a lot of flooding. You realize it can no longer be prevented or controlled. In this photo, we have, in this slide, we have the flooding illustrated. The first picture there is of a flooding event in Somalia. You can see how the towns have been flooded and the likelihood of the property that is going to be damaged because of such a scenario. The second photo on our right is actually the women trying to wade through flood waters in River Nile that broke dikes in the southern Sudan. The last one there is a photo of a farmland that has been flooded. And as much as we look at these photos, we must appreciate that these are the most common scenarios that we are dealing with nowadays and working with, because of the issues blamed to climate change, but more so because we have actually degraded most of our wetlands. And in most cases, you find places that where wetlands have been converted into other ecosystems, such as agroecosystems, urban settings, and such and such. So what are the biophysical indicators for ecosystem assessment when it comes to flood control? So the model considers the quantification of properties or assets that are prone to damage due to flooding. That could be downstream, because they've said there are two scenarios where it could be preventing flooding downstream, or it could actually be preventing the surge of water due to storms under the coastal scenario that could damage properties that are closer to the ocean or sea or even a lake. So the recommended approach is actually to attain this through inventory and quantification of property downstream of the wetland in question. And the model considers this as a derivative of land use land cover mapping, coupled with ground survey to confirm and also be able to account for these properties that are either downstream or are closer to a wetland that is likely to have a surge in water levels. The model allows for the segregation of the downstream properties into 5 known common properties or assets that we were able to come up with when we were working in this project. Number 1, we have the conservation areas. These could be forests, rangelands that have been conserved, and money is being paid towards their protection and conservation. Then we have the residential and business units. We have industries, we have roads, infrastructure, and agricultural areas. And as you understand, and as we have visualized even in the photo in the previous slides, you realize these are the most common scenarios of properties and assets that are likely to be damaged downstream. We must understand this model only applies for wetland ecosystems and not any other ecosystem. The economic assessment therefore employs the avoided damage cost, because if the wetland performs its ability to control the floods, then the property downstream will not be damaged, or the property in close proximity to the wetland will not be damaged. This means that this cost that has been avoided can be accounted for as the value of that wetland. In summary, what we are trying to say that this is a model for the evaluation of flood control as an ecosystem service from wetland. It considers the ecosystem value to be equivalent to the value of all assets in the flood-prone area, just like I have explained. So what are the data requirements? It's quite a long list. We have 17 different types of data requirement because of the intensity of this kind of model in performing its ability to control floods or assess the wetlands' ability to control floods. So number one there, we have the flood-prone area land use raster. And if you check in the guide that has been provided, you'll be able to understand the preparation of this kind of raster, even though in the next slide I'll be explaining a bit of that. There's the surface area of the cropland area prone to damage by floods. There's the length of the road prone to damage by floods. Why are we saying the surface area of the cropland? Because when we look at the production of a crop area, of a cropland area, we normally look at the yield per hectare and then we multiply by the total area that could have been damaged or the total area that is under production. In the Kenyan scenario, and I believe this could apply to most of the other countries, the road construction is charged per the kilometers, the number of kilometers that are being constructed. So sometimes you get to hear that a road is about 1 million Kenya shillings or $1 million US per kilometer in terms of what is engaged in constructing this road. So this is the reason why we are looking at the long length of the road prone to damage by floods by having the units there being in kilometers. We have the number of industries in the flood prone area. This is another asset that we look at. So the number of industries that have been damaged and the area that they occupy is very important for us to determine the damage, the value of damaged property under industries. The same case applies to residential and business units. We count the number, and normally we value the unit and not necessarily the property inside the unit, simply because we are trying to come up with an estimate of the ability of the wetland to control floods. And therefore, we advocate for the method where you look at the property and even for the industries, not the processes taking place or the number of products that are produced at any one given time, because it makes the whole process very complex. And maybe at the end of the day, we may not be able to achieve the estimates that we desire. Then we have the surface area of the conservation area that is prone to damage. This is because, like you saw in the conservation and habitat model, we have a scenario where when government does funding or any institution that does funding, most of the monetary funds are given per hectare, that you require maybe 10,000 US dollars for be able to manage and conserve 100 hectares of forest or even a rangeland. The unit value of crop prone to damage is per hectare in the applicable currency. The unit cost of road construction, just like I've said, is per kilometer in the applicable currency. The average unit of industries, we have the average unit value of industries in the applicable currency. If it is 1 unit of an industry that has been constructed worth 10 billion, that should be in the applicable currency. The same case applies to the residential and business units. The cost of conservation is per hectare, just like I've explained. The surface area of the crop land area prone to damage is in hectares, like I've explained. Same to the length of the road, the number of industries, number of residential and business units in the flood-prone area. This can be done from ground survey to establish the number. And then the area prone to damage by floods, incident rate of floods. This is very important because this is a ratio. And we know that floods do not occur every year. They sometimes occur after a period of time. And that is why the incident rate is very key, because we do not want to be overestimating the value of the ability of the wetland to control floods. So you have to bring in a ratio. What is the frequency? Is it a 0.1? Is it a 0.01 ratio based on historical data that has been able to show the flooding frequencies in a certain landscape? And then lastly, you have the pixel area, depending on the type of Earth observation data that you're using, and the unit is meter squared. So once you have all these met these data requirements Then you can be able to move to the next step of data preparation, where we'll be able to understand how to prepare this data for this particular model. So in the preparation of the input, the flood-prone land use raster, there are two ways in which you can be able to do it. But the most recommended way is to have a land use land cover for the flood-prone area, where you undertake a very good classification to be able to depict the particular classes that are in that landscape. It does not mean all the 5 classes must be there. It depends on the landscape and the landscape and where that landscape is. You might find areas where it's only the conservation area and residential business units are there, or sometimes it's just the industries and the roads, and sometimes maybe the agriculture and the conservation area. So you must be in a position to classify and pick those particular land use classes that are likely to be in this flood-prone area. Alternatively, you can digitize. We have a lot of online gazetteers where you can be able to identify a landscape and digitize the area that is prone to floods. By actually having the vector files, you can digitize the conservation area, the residential area, the industry, the roads, the road infrastructure and agriculture areas. Then this vector file depicting the flood-prone area boundaries can then be rasterized and prepared to actually be used for valuation under the Colwell model. The attribute table of the output land use land cover raster must have a unique ID. And why is this important? The unique ID matches the pixel values columns of the land use land cover raster. And then this particular unique ID will be used to actually insert some more information or data from a CSV file that must be prepared, providing information about these residential areas. And the information that is provided in this CSV file can be visualized in the next slide. So the attribute table of the flood-prone area raster should be as such, where the value is actually a number, a count of 1, 2, 3, 5, depending on the classes that are there. The land use classes, like this one has the cropland, the road, the residential, the industries, and the conservation area. So in the next slide, we are able to see the next data preparation, which also is very important for the flood control model. So step 2 or step B of this data preparation is to know how to prepare the input flood-prone table. And there are 7 instructions that are very key that we must follow. That the table must be prepared in a comma-separated value format, the CSV file that I was talking about. The table must consist of a requisite data for the respective land uses in the flood-prone area captured in the land use land cover. The data required is that the surface area of the cropland area prone to damage by flood, the length of the road must be indicated there, the number of residential houses and businesses, the number of industries in the flood-prone area, and finally the surface area of the conservation area prone to floods. The next slide we will illustrate how the attribute table of the land use land cover raster and then now the input flood-prone table should be, so that they can be able to be matched together and the data in the table can actually find its way inside the raster for the analysis to continue. So like we have said is that the table, the flood-prone area information table must have a unique ID column that matches the unique ID column of the input land use land cover raster, and that specific to the respective land use classes that will be under valuation. If you see in that illustration, you can be able to see the unique ID of the table, where we have captured the unique ID to be numbers 1, 2, 3, 4, 5, the name of the land use land cover, and then the data sets that are required, the crop area, the length of the road, the number of assets, number of industries, the conservation area, and so forth. And this information actually should match with the unique ID should match with the value ID of the land use land cover raster, so that when it is run, they can be in a position to match and the data is picked by the raster. So finally, we are ready to go for the model demonstration so that we can be able to see how the model runs. And finally, once the model runs, we can be able to visualize the output product on QGIS. When you open the flood control model, This is what you expect to see, a flood control model with all the datasets that we have been, with all the dataset inputs, browsers ready for us to input data, just like we have discussed in our slides. So the first one there is the flood prone area land use raster, which we said there are two options in which you can develop it. The most recommended way is a land use land cover classification, where you are able to define the 5 classes or any 1 or 2 or 3 classes depending on the landscape that we'll be assessing. Where that is not available, we have said you digitize and have the vector files for each one of the landscapes, and then that vector file is rasterized to provide the data that will be available for the running of the model. The next thing is the unique ID flood prone area raster. Just like we have said, we need a unique ID for the raster and a unique ID for the attribute table, where the information within these columns is the same, so that the raster can be able to pick up the data from the attribute table that defines the information about the classes within the flood prone area. Once that has been done, then we enter the rest of the information, the conservation area, the number of residential area and businesses, number of industries, the road length, the crop area, the cropland area, as depicted by the attribute table that has been loaded onto the raster. Then we go further to input the cost or the values that will enable us value these landscapes. The first one there being the cost of conservation per unit area. And I believe when we went through the table, we have been able to say the unit area should be hectareage, the average unit value of residents per unit, average unit value of industries, the cost of road we said is usually per kilometer, and then the net value of the crop. The net value of the crop is actually, we are saying that you should have been able to subtract the production cost and give us that net value so that we can be able to have proper estimation. Then we input also the conservation landscape areas, the area for the residential, the industries, and the length of the road and the cropland area. And finally, we have the incident rate of floods. Like I said, that you should be able to know historically that area, the frequency of the floods. So depending on the frequency, that ratio should be put there, whether it's a 0.01 or a 0.5 or a 0.1, to depict for us how frequent is that area prone to floods. Finally, we input the pixel area. And because this data is being done in one landscape that depicts, maybe the landscape is downstream or the landscape is upstream for the cases of coastal regions, then we need to transfer this value that will emanate from this landscape to the raster, and that's why we are loading the wetland raster, and finally now defining the output folder where we would want to find our data. So let us input all our datasets from the folder where you have your input data. So we have the flood control data there, and we have what we are calling the flood prone area. The flood prone area is actually a land use land cover map of built up areas in Kariba, cropland area in Kariba, and also a rangeland area in Kariba, or the forest, to depict a conservation area scenario. So we load these datasets, and then we load the attribute table from the same source. As we have said, is a .csv file. And we have the flood prone table. So you realize the unique ID here for the raster is the values. The unique ID for the attribute table is object ID. These two have the same values in the column, which will now be able to enable the raster and the raster be able to pick all the values that it's supposed to pick from the CSV file. Then we move on to next to fill in the conservation area, number of residential units, number of industries, the length of the road, and finally the cropland area. And then we input the cost. What would be the cost of the conservation unit If let's say, for example, it's 8,000 US dollars per hectare, I'm just using arbitrary figures. You can also do the same for those that are trying out the model. Average unit value of residence, depending on where it is, we can say about 50,000 US dollars. Average unit of the industry, they're usually very costly. We can input a figure. Then the cost of road construction, it could be 6,000 US dollars per kilometer. The net value of crop, which I put around 6,000 US dollars. Then we go further and input the areas. Supposedly the area was 4,500. The area for, and this is information that should be obtained through the ground survey so that you are able to know the exact conservation landscape area. The residential landscape area, which could be 69. I'm just using arbitrary figures. 1,000 for the landscape area for industries. The length of the road could be 800 kilometers. Cropland area could be 450 hectares. And then the incident of flood, I put it at 0.01. Probably the area, the frequency of floods is not so high, so that we do not end up overestimating the ability of the wetland to control floods. Like I said, our raster data is Landsat, so it's 900. Then we input this raster, the wetland raster, that is supposed to acquire this value as a result of being in a position to control floods in that landscape that we are assessing. So the wetland here that should be considered should be actually Kariba Dam, because that is the area that we are working on. So we pick the Kariba Dam TIF. So what will happen in this model is that once it has finished the landscape assessment, it should be in a position to load the values onto the wetland raster. And then we identify the folder where the output should be stored, the output data folder. And then once all these data sets have been loaded, it is ready to run. And we can actually click OK so that we allow the model to run. We have loaded quite a number of data sets over there, so we have to give it time for the entire process to run, and so that we can be able to have the flood control value for our wetland, which is Kariba. The model is at 90%, almost done. It takes quite a considerable amount of time. So if you're running the model, be patient enough to wait for it to run. And once it has finished, then we can be able to visualize the output in QGIS. So the model has successfully finished. Once it has done that, you say OK. And then now we can be able to go and visualize the outputs in QGIS. So we open our flood control output, which should be Kariba Dam, with all the values assigned onto it. We'll have the same value for every pixel on Kariba Dam. So we have the flood control model output 21. That is what you're supposed to load. There you have Kariba Dam with some value. It's the same value because these values are being calculated from one landscape and being moved to another landscape. So once you have loaded it, you can put the color of a wetland to just visualize. And so that is how we have our value for Kariba Dam. This is the first value I believe we are having in the Colruyt model for wetland valuation. So as we bring on more models for wetland valuation, we'll be able to see how we are accumulating the value for wetland. Thank you.